Hello Math 8 to 11 students. Let's begin the second half of the course with Lesson 9, Fermat's Theorem. Fermat's Theorem is based upon the theory of congruence, so I have some brief summary version of the review in congruence here in section 0. But if you feel comfortable, then you can just skip over to section 1. And then section 1 has its own review and summary. 1.1 and 1.3, and let's discuss these. Arithmetic modulo prime versus arithmetic modulo general M, where M is any positive integer. What are the similarities and what are the differences? First, congruent classes, and these are pretty much identical. We can define ZP as the set of all whole numbers less than p, 0, 1, 2, 3 up to p minus 1, or set of all whole numbers less than m, 0, 1, 2, 3 up to m minus 1. Here, p stands for a prime number, you see, modulo prime. Here, m is arbitrary positive integer. This is general modular arithmetic. Either way, the conclusion is identical. We can classify entire Z through the remainder class uniquely, and that's due to the division algorithm, division by P, and also division by M. So other than the characters M versus P, the conclusion is identical. So as for the congruence classes are concerned, they're the same. And then remember these notations, ZP and ZM. In abstract algebra, we define those using equivalence classes and equivalence partitions and quotient set. But here in number theory, we do some easier version. So consider those as just integers from 0 to p minus 1 and 0 to m minus 1 respectively. So those are congruent classes. And so far, we saw no difference. Next, cancellation law. C times x is congruent to y, then c is congruent to 0, or x is congruent to y. So if c is 0, then we have 0 equal to 0, no problem there. Otherwise, we can cross c out, you're going to get x is congruent to y. And this is precisely the same property that works for q or r or z. Rational numbers, real numbers, complex numbers, we can divide freely other than 0. So other than 0, in which case we have 0 equal to 0, we can do the cancellation. Now for general modular arithmetic, it doesn't work like that. We need an additional condition, the relatively prime condition, which I'm highlighting in blue right now. So if C and M are congruent, C and M are relatively prime, so GCD of C and M is 1, then we can cross C out so that we get C is congruent to, X is congruent to Y. And if you remember what we did in lesson 6 and 7, you'll remember that this relatively prime condition yields the division or the multiplicative inverse of C. So we can multiply the multiplicative inverse of C to both left-hand side and the right-hand side. C inverse, they cancel out. And also you can consider this as a generalization of this. You see, P is prime number, so P is relatively prime to everything except for its multiple. So if its own multiple, in that case, is congruent to 0. Otherwise, we have this automatically, so you don't really have to specify it. In any case, the cancellation works every time, in general, absolutely, for arithmetic modulo prime. But in general, we need this blue condition, the relatively prime condition. Remember that. And as for the proofs, well, we can go back to lesson 6, 7. We went through the multiplicative inverse, which came from linear congruence equations, which in turn came from linear Diophantine equations. Remember all those? and which in turn came from divisibility theory. It goes way, way back. all the way back to lesson 2. And that's one way to handle it, but that's a bit too hard. If you just assume okay, all right, there's blue condition, so we can just go ahead and divide, then it works out great. But if you want to prove that, it goes all the way back to linear Diophantine equation and even before that. So that's a bit harder road to prove. Much easier way to prove is to use a Euclid lemma like this. So Cx is congruent to Cy, so left-hand side minus right-hand side is congruent to 0, and then factor C out, and the conclusion is C times xy is a multiple of P, so P divides C times xy. Now P is prime, so it cannot be broken apart into several pieces anymore. This is just a particle. So P belongs to C or x minus y as a factor. So either P divides C or P divides x minus y. And the conclusion follows. And that's Euclid lemma. And I used the explanation of Euclid lemma using prime factorization, but as a matter of fact, the proof of Euclid lemma follows from the Bezout's linear combination expression. Now, in general, what you do is similar. Left-hand side minus right-hand side is congruent to 0, and factor C out, and then m divides C times x minus y. Now here, we already have this GCD of C and m is 1, so no prime factor of m belongs to C, so all the prime factors of m must go to x minus y, and consequently m divides x minus y. That's how Euclid lemma applies in general. Again, I used the prime factorization as a way of explaining. The proof of this Euclid lemma doesn't actually require the prime factorization. It follows from the Bezout's linear combination expression of GCD, if you remember that. Okay, so much for the proofs. And then if you forget about the proof, okay, that's not going to kill you, but still remember those. Arithmetic modulo prime, you can use the cancellation law freely. For general case, arithmetic modulo m for arbitrary positive integer m, we need this blue condition, the relatively prime condition. Next, how about zero divisor? For arithmetic modulo prime, there's no zero divisor, no non-trivial zero divisor, to be a little bit more precise. So a times b is 0, then either a is 0 or b is 0. We're taking the contrapositive. If both a and b are non-zero, then a times b cannot be 0 either. How about the zero divisors for general case? In that case, as before, we have to have this blue condition, the relatively prime condition, so that you can use the cancellation. How about the proof of this? Well, proof is pretty simple as a matter of fact. One way to do that is to divide by A or divide by B, and it works as a matter of fact, but as I said before, if you are going to use this multiplicative inverse, that actually goes back long way, all the way back to linear Diophantine equations and beyond. So it's hard to follow. An easier proof is this. A times b is congruent to 0, and rewrite 0 as a times 0. And then we can apply the cancellation law, crossing out a so that we get b is congruent to 0, otherwise a is congruent to 0. Or you can do the same thing the other way as well. 0 times b is 0, and then we just cross out b so that we get a is congruent to 0 or b is congruent to 0. In any case, it works out, and that's coming from this cancellation law. The proof of the general case is pretty much the same. By the way, by symmetry, we can have the other expression as well. And by this GCD condition here, under this condition, A times B is 0, and then 0 can be rewritten as A times 0 as before, and then crossing A out. Yes, I can do that under this condition, under this, because the cancellation law applies. And then as for the second one, yeah, you can set up and do the same thing. By the symmetry, it should work as well. So the cancellation condition and zero divisor condition, we went through those. And what's the moral of the story? And for P, everything works out all the time, absolutely, no problem. In general, we need that blue condition, that relatively prime condition. Finally, multiplicative inverse. Yeah, multiplicative inverse always exists and it's unique. Multiplicative inverse always exists? No, not really. When GCD of A and M is 1, in other words, A and M are relatively prime, then it always exists. Oh, excuse me, I forgot the uniqueness notation. It always exists uniquely. As a matter of fact, you can prove like this. Relatively prime if and only if the solution exists. And then you can prove that the solution is unique later on. So if you put that together along with this uniqueness, then you're going to get that. So we have unique solution. And all right, the proof of that goes back to lesson 6 and lesson 7. And that goes back to lessons, all the way back to 2. All the way back to linear Diophantine equation and so on. So in any case, if you're going to apply general modular arithmetic with all those nice things, you have to have that relatively prime condition. For primes, you don't have to worry about it because prime numbers are relatively prime to everything except for its own multiples. So keep those in your mind and let us express Fermat's theorem in the original form and then extended form by Euler. How does the original form look like? If P does not divide A, then A to the P minus 1 power is congruent to 1 modulo P. In other words, if A is non-zero mod P, then A to the P minus 1 power is 1. In general, A to the P power is congruent to A. You see here, multiply A to both left-hand side and right-hand side, we're going to get this. And also, in a special case, when P divides A or A is 0, then you get 0 is congruent to 0. So this one works all the time, but A is congruent to 0. That's a trivial case. The overwhelming majority is this one over here. That's known as Fermat's little theorem, but in this course we are going to call it Fermat's theorem because we are not going to consider Fermat's great theorem in this course. Now, a little bit more generalized version by Euler is this. We have this GCD condition, this blue condition, this relatively prime condition. Hey, what a surprise. And then A to the phi of m power is congruent to 1 mod m. What is phi of m? It's the number of positive integers less than m that are relatively prime to m. So for prime numbers, phi of p is p minus 1. Everything less than p other than 0 is relatively prime, so we have p minus 1. Minus 1 is due to 0, but in general there are some factors, and then there are some numbers that show some that share some prime factors and so on. So it's going to be less than m minus 1 in general. So we have phi of m. So you can consider this one is a generalization of that. And those are Fermat's theorem and its extended version. We are going to talk about the proof and applications in the next videos. For now, let's stop here.